In this video, I'm going to talk about priors, likelihoods, and posteriors, and I'm going to present a simple Bayesian workflow for conducting studies. So this is the workflow for Bayesian modeling. These 4 steps are required for any study that I conduct. The first step is to specify a model for your data. The second step is to set priors for all of the parameters in that model. Step 3 is to find a way to sample from the posterior distribution. And step 4 is to summarize the draws from the posterior distribution to engage in statistical inference. Step 1 is to specify the model. So here's a model I've specified, a very simple model. Maybe I've got y sub t, which we could assume to be maybe some measure of firm performance in time periods t. And that's a function of x sub t, which maybe is a measure of utilization of some resource in time period t. And then I've got epsilon t, which is our error distribution. We assume that's normally distributed with mean 0 and some variance term. Okay, so that could be a model that I would specify. Maybe not the most clever model or the most accurate model, but that's a model. And just like in frequentist inference, you have to justify the choice of your model. So what theory exists that would suggest that we need to include this covariate xt? Why didn't we include any time dependency? So why is y in time period t not also a function of x in time period t minus 1 or y in time period t minus 1? So justify the choice of your model the same way you would have to justify the choice of a model if you're conducting a frequentist study. Step 2 is once we've specified a model, we have to set priors for all of the parameters in that model. And so in this case, I have 2 parameters. I have betas, and I have a variance term sigma squared. And I could specify a prior for beta that is normal with mean 0 and variance 100. This is a very diffuse prior. Referred to sometimes as an uninformative prior, or better yet, as a weakly informative prior. When we specify a prior this diffuse, we're effectively saying that we don't have any legitimate prior knowledge about what beta might be. And so we're going to let the data speak for themselves by basically taking the prior out of the equation, in the sense that the prior is not going to exert much influence on the resulting posterior distribution. And the same is true for the variance term. We specify the variance term as coming from an inverse chi-square distribution with 3 degrees of freedom. Given the variance in our data, this is actually quite a diffuse prior. And we specify inverse chi-squared because it's conjugate in this type of model. So it facilitates, just makes computation a lot easier in this context. And so in this case, we have to justify the choice of this prior. Why does it make sense for me to specify a prior that doesn't really bring any additional information to the table? Other ways of picking priors might be to use a past study that uses sort of similar covariates and relationships to try to specify something that's a little more precise. If I were to do that, it would raise the question, how much influence does that prior have on inference? Is my inference being driven by the data I've collected, or is it being driven by the prior? One way to deal with that critique is simply to use alternative priors and just to see how robust your results are to prior specification. And that tends to be a fairly easy exercise to engage in. And so I start by specifying my likelihood. I've set priors for my model. The next step is to find a way to sample from the posterior distribution. And so in this case, I have effectively a regression model with a standard set of priors. I can use a CAN software package. Specifically, I'm doing this in the R statistical computing environment, and I'm using a package called BayesM, which is a package that has a lot of routines for doing Bayesian inference in contexts that we use in marketing, including a bunch of regression settings. I'm using a routine called R-unireg Gibbs for a univariate regression. It uses a Gibbs sampler to draw from the posterior distribution. And reflected here are draws from that posterior distribution. So our model's converged. It's sampling quite nicely. Once I've found a way to sample from the posterior distribution, I can move on to step 4, which is to summarize draws from the posterior. And I've done that graphically here, right? I show the empirical distribution of beta naught and beta 1. And from those empirical distributions, I can compute all sorts of quantities. And so I can compute the mean, which is 1.3 in this case. The standard deviation is 0.11. I compute a 95% interval. We refer to these as sort of, we call them credible intervals. They're sort of akin to a confidence interval. But my interval ranges between 1.1 and 1.6. And I could use this if I wanted to engage in something akin to a hypothesis test in a frequentist setting. So if I wanted to test my beta knot parameter against a point null of 0, I can look at my interval and it doesn't span 0. And so I can say, well, I'm 95% confident that the true value of this parameter lies between 1.1 and 1.6. And so, if I'm using something akin to an alpha of 0.05, I would say that, I would reject the null, right? So beta knot clearly is not equal to 0. And the same is true for beta 2. So I summarize my draws for the posterior accordingly. And that's the process. And so we specify a model, we specify prior distributions, we find a way to draw from the posterior distribution, and then we can conduct inference by summarizing those draws. Two things to keep in mind are that we have to justify the assumptions of our model, and we especially have to justify the choice of the prior distribution.